Welcome to my virtual poster. In the next few minutes, I would like to present an application of the real-time haptic quantum chemistry algorithms developed by the Reiher group in recent years that might differ from computational chemistry research that you are used to. In my PhD project, I am working at the intersection between computational chemistry and learning sciences. I will start by introducing you to the mind of a first-year chemistry student and will then sketch out in what ways the haptic quantum chemistry framework might enhance their learning experience. We have measured the knowledge of chemistry students first by sending out a test tackling the concepts potential energy surface, force, and reactivity. We then also had a few interviews with students who solved the test while thinking aloud. As you can see, although the potential energy surface is closely connected to the 2D energy graphs that the students encounter more or less daily, the transfer to 3D potential energy surfaces is not trivial at all. On the right-hand side, you see the percentage of students who chose this answer. Below, you can see two excerpts from the interviews. What seems to be a salient feature when it comes to understanding chemistry is the ability to connect symbolic and molecular representations. What does it mean for a molecule to have potential energy? And how can we represent this with formulas? Of course, I have taken extreme examples here, but this goes to show the hugely heterogeneous audience that a chemistry lecturer encounters and therefore motivates the goal to find innovative ways to enhance the learning experience. As you know, quantum chemical calculations are usually taking too long to have a real-time interaction with the system at hand. The solution to this problem is surprisingly simple. We introduce a surrogate potential which makes the environment appear smooth until the next electronic structure calculation, in our case a semi-empirical calculation performed by Science Sparrow, gives us the next result. This surrogate potential is nothing but the second-order Taylor series at the position of the last calculation. What this means is that every atom gets its own temporary well, according to which it relaxes until the next calculation is done. The gradient of this potential is, of course, also minus the force. As you can see here in our environment, the user can drag and drop the atom, and the motor in the haptic device furthermore allows them to feel the forces that operate on their picked atom via resistance. This now allows to translate between the three major levels of understanding that chemistry has. For us chemists, the connection between an equation, the behavior we see in the laboratory, and the molecular behavior is often straightforward. This is one single chunk of information for us. For a student, this can create difficulties as they have to actively make the connection. Here, the haptic device acts as a scaffold to the student. By feeling the force, the equation shown here can be experienced in the macroscopic world. Moreover, the theoretical framework Embodied Cognition argues that we are not only learning with our minds, but that how we experience something plays a huge part in the learning process. Like a child that learns quicker what a cow is by playing with a toy cow or by petting a cow instead of just looking at an image or being described what it is, a student might also be able to profit from experiencing even abstract concepts. We will explore this hypothesis further in a planned learning study. Until then, let's chat, or please follow up via email if you have any thoughts, remarks, feedback, or questions. Thank you.